So, hopefully you can see this on your notes, because for whatever reason it's not very beautiful on the screen. So, we're going to do an example of Fourier series analysis, and we were going to take this as our starting point. So I'm going to talk about this again for just a minute. Okay. So let's talk through it. So just for me, I can't focus. So if you've got a square wave, so this red thing, the thing you guys can actually see on this, is a good old-fashioned square wave constructed from the sum of some number of sinusoids, but not obviously an infinite number of sinusoids. So it doesn't get perfect representation from it. But if we wanted to, so first of all, a square wave is a periodic function, correct? And for periodic functions, we can write Fourier series. So that's what we're going to do. This square wave can be thought of, just as any periodic function can be thought of, as a sum of a bunch of sinusoidal components that we can find from the Fourier analysis. Okay, so each of these components corresponds to a frequency. The lowest frequency is the fundamental frequency, right? That was what we called it. And the fundamental frequency is the same as the frequency of the original function. So the frequency of this square wave, the angular frequency, if we want to be precise about it, is 2 pi over t, which is, so t is this length. Omega 1 is the frequency corresponding to that length of time, that interval of time. So we have a fundamental frequency, which is the first component that you can see drawn here. So I'll draw it in black. Woo. And that one has the largest amplitude. So that's why on this axis we have this spectral amplitude shown as being the largest. And then the next harmonic is at a higher frequency, a multiple of, it's getting worse. At a multiple of the fundamental frequency, an integer multiple. And that amplitude is a little smaller. It didn't have to be smaller, but it's smaller. It has to be smaller just because this is the function we're representing. So once you do the Fourier analysis, you discover that amplitude is a little smaller than the first amplitude. Sometimes they will temporarily increase before they end up dropping off at higher frequencies. So it isn't always monotonically decreasing. Sometimes the amplitude is positive and negative, positive. Sometimes it's actually, in this case, there's some zeros in there that we're not showing. So the idea, though, is that you take these, and then, way out here we've got this little tiny one, all the way down. And so if you add these up, whoa, that was not a good direction. There we go. If we add all those up, sum those up, we get this red wiggly line, okay? And the more and more you sum up, the closer and closer you get to your representation of the square wave. So we can think of the square wave as either being this time domain function in red, or we can think of it as having this frequency domain representation, which is this spectral amplitude with the bars here in frequency. Okay. So that's kind of the idea of Fourier analysis, Fourier series analysis. And that really, I just want to stress again how the biggest and most important aspect of this is that we can start to think of time domain signals in the frequency domain as being composed of a bunch of frequency components. Okay? And the frequency components are specifically these harmonics, and they have certain amplitudes associated with them. And we can look at the spectrum. So this was what the graph would look like in time, right? And then this other axis here is frequency. So we could draw that flat as well, and it would just look like these bars, right? That are evenly spaced out. So that's the frequency domain representation. So that's what we're going to do. We're going to actually take this square wave, and we're going to do the analysis on it to find the line spectrum. I showed this to you, but how did I find this? Well, through finding the Fourier series components. So, compute the first 5 harmonic amplitudes that represent the line spectrum for a square wave in the figure above. So we're actually going to compute what these heights are, okay? Because we can. Okay, so I didn't say what the amplitude of the square wave was, so let's assume square wave amplitude of 1. So let's compute AN. So AN, if we go back up here and look in our definition of the trigonometric form of the Fourier series, we used AN, right? And it has this formula, 6,1. So we can just plug in to this, right? I didn't give us a t value for the period for this square wave. We're just going to use t. We're just going to use it in the calculation. It's fine. So AN equals, from the formula, 2 over t times the integral from, so you have to integrate over one period. Let's just use this negative t over 2 to t over 2 period. We could use from 0 to t if we wanted as well. That would be fine. Sometimes there's a more convenient choice for the period and a less convenient choice. So especially in this sort of piecewise definition of something, you could integrate over, for instance, the period from here to here, but then you'd have 3 different intervals that you would have to integrate over. But if you just chose from, so this is time equals 0, if you choose from 0 to t, you have 2. If you choose from negative t over 2 to positive t over 2, then you get, so this is t over 2, right? Then you get just 2 intervals. So there's usually a more convenient period to integrate over, so I would just choose that accordingly. Whatever's easiest is my motto. Y of t. So y is this square wave, so we'll call it y. Call it anything. Cosine of, so omega n t dt. And we're going to ignore the fact that we're not using a dummy variable of integration here, but it's fine. So our omega n, of course, is just 2 pi n over t, right? So here's our an. We need to integrate over some period. We chose negative t over 2 to t over 2. And this y, this square wave, has 2 constant values that are easy to integrate over independently, but are hard to integrate over if you try to write one function that described it. So we just do it piecewise. We could integrate over this interval first, and then integrate over that interval second. That's our preferred method, right? So we said the amplitudes are positive 1 and minus 1. So that means that we have t over 2, splitting it into 2 different integrals. T over 2, I'm to integral from negative t over 2 to 0 of, well, y of t in that interval is what? So from 0, so this is our 0. So 0 to, so negative t over 2 to 0 is negative 1, right? Good. So negative 1. And cosine of omega n t dt plus 2 over t times the integral from 0 to t over 2 times, what is y of t during the interval from 0 to t over 2? 1. Cosine omega n t dt. So this is just integrating over cosine in each case, right? So we get the integral, so we can take the negative sign out front. And in fact, what we see is we have the integral from negative t over 2 to 0 of cosine omega n t with a negative sign out front. And then we have the same integral from 0 to t over 2. But cosine's an even function, right? And so if you integrate over some negative region that's symmetric with a positive region, you're going to get the same value. But since there's a negative sign out in front of the first one, they have to be equal and opposite to each other, right? So they add together to get 0. So, and this is because, so we say because cosine is even. And in fact, it can be shown that for any even function, so this is something that, this is bonus for being here at the lecture. You get to know this shortcut on an exam. If you have an even function, so because cosine's even, this came out to be 0. But we have, the original function is an odd function, okay? An odd function yields odd function y always gives an equals 0. That is a nice little shortcut. So if your y is odd, you don't have to go through the integration to find out that it's all the an's are 0. Okay, and then the opposite is true if you have an even function. So I'll say this: even function, y always gives bn equals 0. So if it's an even or an odd function, you only need to compute either an or bn. You have to know which one. You could just guess, and if it comes out to be 0, you could be like, damn it, I missed the shortcut, but at least I'm still on the right freeway. Because then you can just compute the other one. You just found out that that one was 0. Okay. So now we've got to compute bn, right, which, spoiler alert, it's not going to be 0 in all cases. So bn is equal to 2 over t. That was integral from negative t over 2 to t over 2, y of t, so this is just from the definition, sine of omega n t dt. So once again, our y is nice to split up from negative t over 2 to 0 and from 0 to t over 2. So we'll do that again. So this all looks very familiar. I'll pull the negative sign out front here in one step instead of in two this time. And sine of omega nt. You guys hopefully don't get too bothered by my lack of parentheses on this term. It's really common that if a trigonometric function shows up with an angular frequency in front of it and a t, that we will interpret this to be implied parentheses, and we don't put the parentheses. Even though it's a little ambiguous, it's very common practice, so I do that frequently, just to get you guys used to that notation. And also, it looks a little cleaner not to have all these parentheses around. So it appeals to my aesthetic, so I like it. Sine of omega n t dt. And at the end of the day, what's important is that it looks good. Okay. You heard it here first. Jacob.
Because the function is just 1 or negative 1, you pulled it outside. You omitted it from the inside.
Yeah, so in the last step when we were computing an, we put in negative 1 here and we put 1 in here, but we saw that that just turns this one negative, and you can pull the negative 1 out if you want. So I just did that step at the same time. I pulled the negative sign out. So yeah, I mean, you could leave it in there. So negative 1 and then positive 1. What the key is that they're constant during those intervals, and we can put the constant in, and then you can pull that constant, whatever it is, outside of the integral, just as you can always pull a constant outside of an integral. So we've got this term, and in fact, simplifying this is not super hard, but it takes a few steps, and I don't want us to get caught up in a lot of trig. So, but there is a nice expression that you can develop for this if you just go through a couple steps of trigonometry after. So you do the integral of sine. I know you guys can all do that, so not too worried. It's 1 minus cosine of n pi, and I'll put parentheses around this just to be clear. Okay, which you can define in a piecewise way, which is sometimes useful to do with these trig functions. Because whenever n is even, so for n even, then you're going to have, so cosine of 0, cosine of 2 pi, cosine of 4 pi, etc. Those are all 0, right? Wait, yeah. Even? Is that right? Oh yeah, no. Cosine is 1, and then 1 minus 1 is 0. It's like, that doesn't make sense. Cosine is definitely not 0 at 0. Cosine is 1 when n is 0 or when n is 2. But 1 minus that is 0. Cool. I like it when I'm not wrong. That's great. Okay, and it's otherwise, it's 4 over n pi, and you can do a little bit of simplification. So when n is odd. And n has to be an integer. So it can only be even or odd. Okay, so we've got our BNs. Every other BN is 0, but every other BN is non-zero as well. So therefore, we can compute, so we want to compute our harmonic amplitudes, right? So we define that up here in equation somewhere. Did I miss it? There it is. Harmonic amplitude. We're going to use 610 because we have the trig form. We did the trigonometric Fourier series analysis. So we have the ANs and the BNs. All the BNs, all the ANs are 0 and the BNs, some of them are 0. But we want this. So when all of the ANs are 0, this is just the square root of BN squared, which is just the absolute value of BN. So that's what we're going to do here. And so we say Cn is equal to square root. So I should make that C a little bigger to make it clear that's capital. Cn is equal to square root of AN squared plus BN squared. So C0 is 0 because 0 is even. C1 is 4 over pi. C2 is 0 because 2 is even. C3 is 4 over 3 pi. That's a 3 pi. C4, since it's 4 is even, it's got to be 0. And C5 is 4 over 5 pi. So if we go back to our pretty graph here, what we've computed are the first 5. So 0 is 0, so we didn't count that. 1, the amplitude was, so I'll just write up here, it's kind of hard to see on the graph. So C1, actually I'll put it below, C1. And then C2 is 0, so that's not really included in this. C3, C4, and then C5. So that's as far as we computed, C5. And we could keep computing from there. So we've got our spectrum, and we would often not draw it like we drew it in that one, like cool 3D way. We would just draw it like this. We would say, here is omega, here is our harmonic amplitude, Cn, here is our, so omega 0, omega 1, omega 2, omega 3, omega 4, omega 5. And then we've got our C0 is 0, our C1 is 4 over pi, so C1, and then our C2 is 0, and then our C3 is, well, it's like a third, right? So it should be a little shorter than that. Is 4 over 3 pi, and then 0, and then 4 over 5 pi. Yeah, and you can just keep going on. So this is the frequency spectrum. So this is the spectrum. And there's a device that shows us this. And the device is called, what do you guys think? So actually, it's funny. So oscilloscopes typically show you the time domain, but nowadays oscilloscopes can do something that traditionally was not done by oscilloscopes. That is show you the frequency domain. And the traditional instrument, though, and still remains the gold standard for looking at the frequency domain, called the spectrum analyzer. So, makes sense, the spectrum analyzer, right? So, yeah. Sorry?
You had me on the edge of my seat.
I know. It's called a Tamagotchi. No. Surprise, it's actually useful and used a lot now. I don't know. I heard that there's like a new thing that's kind of like a Tamagotchi now. That's like better. I don't know. How could you improve on that? It was so great.
Some kind of app on your phone.
Yeah. It's called All of Your Facebook Friends. Okay, so, all right. Any questions on Fourier series, all that good stuff?